Okay, so the next thing we're going to talk about is one of the first interactions of light and electrons that give us some information about the composition of one of those two properties. First actually being light itself. And this is an explanation of what is known as the photoelectric effect. So what happens is that for some materials known as photoelectric materials, when incident light strikes the surface, what happens is that electrons are kicked off or emitted. So light coming in strikes the surface, electrons are emitted out. Okay, collectively known as the photoelectric effect. If you hook this up to a current meter, of course you can determine the current or charge per unit time that strikes a positive terminal when incident light is being struck on this. Striking the photoelectric material, that is. Okay, so it turns out that at the turn of the 20th century, this experiment was being studied quite vigorously by a lot of scientists, and what they were looking for is they wanted to try to figure out why light was emitting these electrons when it struck the surface, and more importantly, and what we'll focus on, is what aspects of light cause this emission of electrons. Okay, so if you think about what we discussed so far in terms of light, some of the properties of light that we can discuss, of course, are amplitude and wavelength or frequency. Okay? Now, you know, if we change the wavelength, we're affecting the frequency, so we only need to look at one of these variables. So what we need to discuss is see how the effect of amplitude or the effect of frequency affects the emission of electrons from a photoelectric material. Now, what they did was they set, scientists set up 4 experiments to try to determine how these two variables affected this phenomenon, and they of course set up 4 experiments so that they could utilize low intensity, meaning low amplitude light, and both low and high frequency light. Okay, they also looked at very bright light sources. High intensity, high amplitude light sources, and again both low and high frequency light. Now at the time that these experiments were being conducted, most scientists thought that the amplitude was the best indication of the energy of the light source. The brighter the light, the more energy the light was imparting. And that is somewhat true, but what they didn't anticipate was the effect of changing the frequency had on the energy of a light source. Okay, so as it turns out that if you just think about amplitude determining energy, you would think that both experiments 3 and 4 would produce electrons or emit electrons from a photoelectric material, and that perhaps the frequency wouldn't determine much difference. And they also hypothesized that a low intensity light in experiments 1 and 2 could emit electrons, that there might just be a sort of build-up period where that the absorption of the light would build up and eventually emit electrons. Now it turned out that that was not true. Even with a low amplitude, low intensity light, there was no build-up time. It turns out that what really determined whether or not an electron was emitted was the frequency. And it turned out that high frequency was the major factor on what determined or what caused the emission of electrons from photoelectric materials. It didn't matter if you had a very dim light bulb or a very bright light bulb. As long as you had high frequency light, electrons were emitted. And it turned out that there wasn't even a lag time for low intensity light. As soon as you shined high frequency light on the photoelectric material, whether it was low or high intensity, electrons were emitted. And this confused some scientists until a hypothesis, or an explanation rather, was put forth by this gentleman, of course, Albert Einstein, pictured here on the left, about the time he was doing these experiments in his younger days, and of course the more infamous or famous photograph of his later years with a little bit crazier hair. What Einstein did was build on the explanations, or build on the hypothesis of Max Planck, another German physicist, who previously hypothesized that energy itself was quantized or came in discrete steps. Einstein further proposed that not only energy, but light is also quantized. Or comes in small packets. He called these packets quanta. And that has sort of given way to a more proper or more popular name for the packet of light, and that is the photon. Okay, and a photon actually describes light as a particle. Okay, not only does light act as a wave, as we previously discussed, it also has particle-like properties. Particle of light. Okay. He additionally utilized a constant that Max Planck was using to describe the quantization of energy, to describe the energy of light. Okay, and so what Einstein did was create this equation to determine or calculate the energy of photons. And you can see that here we have the frequency, and h is actually a constant, Planck's constant, which is 6.626 times 10 to the negative 34th joules seconds, and capital J is joules, unit of energy. So from this theory or explanation of the photoelectric effect, we now know that particle, in addition to acting or having wave-like properties, has particle properties, and this is now known as the wave-particle duality of nature, as we'll see further in our discussion of the electron. And we also have an equation to calculate the energy of a photon, which we now know is really based on the frequency. And it turns out that the amplitude actually describes, or how bright a light source describes how many photons are being emitted by that light source, not the energy per se. Okay, so here's back to our electromagnetic spectrum. And what we want to point out here is that we also, in addition to frequency and wavelength, we can also look at this as a function of energy. And reading this from left to right, we go from low energy to high energy. And that relationship we can look at as with our equation. Okay, we can see that because Planck's constant is a constant, if we increase the frequency, the energy of the photon also increases. So frequency and energy are proportional. And because frequency and wavelength are inversely proportional, as we previously stated, we now know that wavelength is inversely, or we can infer that wavelength is inversely proportional to energy. So, radiation with very, very high frequency is also high energy, and radiation with very, very small wavelengths is also high energy. Long wavelengths are associated with lower energy, and small frequencies or short frequencies are associated with lower energies as well.